So to pick back up where we left off on the previous lecture, we had finished looking at the salient features and definitions of our three intermolecular forces. Those would be dispersion forces, dipole-dipole interactions, and hydrogen bonding. Now, dispersion forces were the weakest intermolecular force, but they are exhibited by all particles because they are resultant from temporary dipoles that are exhibited from instantaneous imbalances of electron density within particles. And since all particles have electrons in them, all particles must bear dispersion forces. The next intermolecular force were dipole-dipole interactions, and these are an intermediate level force, much stronger than dispersion forces, and they are exhibited in any molecule which bears a dipole moment. And lastly, hydrogen bonding. Hydrogen bonding is the strongest intermolecular force, and it is only exhibited by covalent molecules containing either an OH, an NH, or an FH covalent bond within them. So we are going to shift our focus briefly from liquids into solids, because this unit of study is the solids and liquids unit. We'll start looking at solids and a particular type of solids. There are two types of solids, one of which we'll be looking at in more detail. There are amorphous solids, which implies that the particles don't have a pattern or a lattice to them. But the ones that we're going to be more associated with are called crystalline solids. They form a crystal in which the particles are always in a predictable pattern or array. There are three types of crystalline solids which we are going to be associating ourselves with: molecular solids, ionic solids, and atomic solids. Now, the basis of all of these, how we split them up, are based on their type of particle, and that type of particle is right within the name. Molecular solids, the composite units or particles, are molecules. Ionic solids, the composite units are formula units, cations and anions. And in atomic solids, well, they are simply made up of atoms. Now, specifically with atomic solids are the only ones which we would express as elements, because since the composite units are atoms, we are assuming that all of those atoms are the same. So basically, any element would be considered, in its solid form, would be considered an atomic solid. So there are many things that compare and contrast these three types of crystalline solids. We are going to look specifically at melting points. Now, melting points, just like boiling points, remember, if we had a higher boiling point, well, we had a higher force, stronger force rather, holding those particles together. A lower boiling point meant a weaker intermolecular force holding those particles together. The same can be said for solids and their melting points. The higher melting point means there is a higher or a stronger force holding the particles together. Comparatively, with a lower melting point, that means there's a weaker force holding the particles together. And when we look at this, we see that ionic solids are high melting. They're very high melting compared with molecular solids, which by comparison are lower melting. It's only in this comparison that we're using a low melting and high melting, and we're going to talk about why that might be. When we think of an ionic solid, we think of ions that are held together by these forces. The stronger the force holding these ions together, the higher the melting point. Well, let's think of that force, which is holding, in this case, this is a crystal of sodium chloride. What is the force that is holding the sodium cations and the chloride anions together? Well, it is an ionic attraction. It's literally an ionic bond, one of our types of chemical bonds. Now, so a chemical bond is one of the strongest forces known. It eclipses the strength of any of our intermolecular forces, even hydrogen bonding. So really, the ionic solids are so high melting because their ions are held together literally by very, very strong ionic chemical bonds. So we can contrast this with the lower melting points on molecular solids. If we look at molecular solids, we're talking about molecules being the composite particle. And in this example here, we have water. Here's some water molecules that are held together, in this case, by not chemical bonds, but rather by intermolecular forces, those red dotted lines we see there. Now, since this is water, certainly the intermolecular force that is holding them together, since they bear OH bonds, are hydrogen bonding, the strongest intermolecular force. However, even the strongest intermolecular force cannot hold a candle to the strength of a chemical bond, which is what we have with the ionic structure right here. What holds the water molecules together in a solid ice, in this case for water, are only intermolecular forces, and thus that makes them lower melting. Now, when we look at our final one, this is sort of I look at as a miscellaneous file, the atomic solids. Our atomic solids can really be a mixed bag. They're everything that are not molecular solids and ionic solids. They are essentially our elements. And our elements, as we know, at ambient temperature and pressure, some can be solids, some can be liquids, and some can be gases. However, any of our elements, taking out enough energy from them, bringing their temperature down enough, will eventually crystallize into a solid. But it's just all about the forces which hold those atoms together, which give this great diversity in what we're calling the variable melting points here in atomic solids. They're so variable, we really need another whole grid here that I'm showing you to define atomic solids. So let's take a look at that. Atomic solids, because they are so diverse, require a brand new type of grid to look at. Atomic solids themselves can be brought down, or can be brought into three categories: covalent atomic solids, non-bonding atomic solids, and metallic atomic solids. So let's take a look at these. Now, one would think that a covalent atomic solid would be an element, because they're all the same atoms, remember, held together by covalent bonds through the entire solid. That's really saying something. Moving over one, we have our non-bonding atomic solids. Now, these are held together by dispersion forces, our weakest intermolecular force. And lastly, our metallic solids are held together by metallic covalent bonds, or I'm sorry, metallic chemical bonds. So we have these three, and the way we compared them last time was by melting point. So let's look at these atomic solids held together by their melting point. The covalent atomic solids are considered very high melting, to the point where they almost do not have a melting point. They actually they go to a point where they decompose. Because if you think about it, with covalent atomic solids, these are covalent bonds, the strongest chemical bond holding the particles together, those atoms together. What might be a type of, an example of a covalent atomic solid? Well, diamond. Diamond is the hardest substance known to humankind, and what diamond is an allotrope of carbon. It's simply carbon put together. So if we look at the way a diamond is put together, it is three-dimensional carbon. If we look at this, and those carbon atoms, it's all the same type of atom, they are held together by covalent bonds. Thus, if we were to heat up a diamond, we would have to heat it up to the point where you're actually overcoming the attraction of covalent bonds, the strongest force holding particles together. And that's simply not done. There actually is no such thing as liquid diamond. As we heated up a diamond, it would decompose into carbon, essentially into soot, before we could overcome those covalent bonds. So to say diamond is high melting is really an understatement, because you cannot get a sample of diamond, that allotrope of carbon, hot enough so that it actually melts into a liquid. By comparison, we have our next door, we have our non-bonding atomic solids. So these are still elements, but normally they don't have any chemical bonds holding them together. They, for instance, an example of this would be solid xenon. Now, xenon is one of our noble gases. We consider it a gas because we're only usually associated with it at room temperature. But taken enough energy out of a sample of xenon, if we brought that temperature down, kept on bringing it down, it would eventually condense into a liquid. And then if we drop the temperature of that liquid xenon down further, it would eventually crystallize into a solid. That's something we would never see. It's very close to 0 degrees Kelvin, but it can be done. So if we saw something as exotic as solid xenon, we would have to say, well, ask what are the forces holding those particles together? Now, if you'll remember, xenon is a noble gas, and noble gases were one of the two types of particles that only bear dispersion forces. So in this case, we have our solid held together by the weakest intermolecular force, our dispersion forces. So in contrast to the very high melting, if you can even get there, high melting temperatures of covalent atomic solids, really the opposite of that would be our non-bonding solids, atomic solids. An example of that would be solid xenon, which have extremely low melting points. Now, just as atomic solids seem to be sort of the miscellaneous file of our crystalline solids in general, because they weren't ionic solids and they weren't covalent solids, our metallic atomic solids are in itself its own miscellaneous file, because we're talking about a metal here. Since our atomic solids are all the same type of atom, the same type of elements, we're talking about metals, metallic elements. And as we may know, some metals have, by comparison, very low melting points. Something like mercury, which at room temperature is a liquid. And that is contrasted by other metals which have exceedingly high melting points, such as something like tungsten, which forms a filament in an incandescent light bulb. That gets so hot that it glows so very, very brightly, but it still will not melt. It retains its solidity. So we can put gold in there, we can put tungsten, we could put mercury. They're all considered metals, but we really can't define them based upon their melting point, because that melting point is all over the map. So let's shift gears here and move from solids back to liquids. We're going to look at liquids, especially a concept of liquids, which is evaporation. When liquids evaporate, if I take a beaker of water and I put it on the counter and I take note of it, and I come back in, say, 5 minutes and look at the height of the water in that beaker, it's not going to have moved. It's going to look exactly the same. However, if I came back after 2 weeks and looked at the level of water in that beaker, well, a lot of it would have been gone. This we understand as evaporation. Over time, a liquid will be converted into a gas without having to be boiled. It happens sort of over time, one could say spontaneously. And we're going to look at evaporation of liquids from, again, a particulate standpoint. And when we think of the concept of a liquid from a particulate standpoint, if we looked at that, if we could see inside the particles, the molecules or what have you, of a liquid, we would see that they're always in motion. And sometimes that motion is faster for one given particle and is slower for another given particle. And these velocities, if you will, are part of what is known as kinetic energy. They're kinetic energies. The higher kinetic energy means a higher velocity to that particular particle. So we're going to look at evaporation now from the concept of the movement of the particles. In any liquid sample, some of those particles are really zipping around, and some of them are not moving very fast at all. There is a range, a wide spectrum of different velocities within there. So if we could graph this, we could look at a particular at a particular temperature, a graph showing the relative velocities of all of its particles, for instance, right here. So on the x-axis here shows the increasing kinetic energy of a particular sample of the particles. And on the y-axis, that shows the fraction of those molecules or those particles which are at a particular kinetic energy. So now notice, and I'll try to trace out this bell curve again, if you will. At a given temperature, some of our particles in the liquid are moving very slowly, like over in here, very slowly. Some are moving very quickly, like on the other end of this bell curve. Most are moving at a sort of a mid-range mean velocity, but it's really at any given time a liquid will always have these very low velocities and very high velocities. And it's the particles which are at a very high velocity at a given time that we want to focus on. Velocity is kinetic energy. It says as velocity increases, the kinetic energy of a particle increases. So that can eventually overcome the energy which is holding together these particles by their intermolecular forces. Once the kinetic energy of a particle, if it's moving fast enough, overtakes and transcends a particular threshold of speed, it then achieves escape velocity, meaning its kinetic energy is greater than the energy being used or being expended to hold those two particles together, and it can erupt into the gas phase. And when that happens, evaporation is happening. Now, so this distribution of particles within a liquid is heavily dependent upon temperature. So notice there are two different curves in here. On the first curve, at a lower temperature, we have this curvature, where no matter what, there is always a certain fraction, there it is, at or above escape velocity. That is the fraction that can evaporate at any given moment. Fair enough. Well, when we heat a sample of liquid up, what happens to its relative velocities is we flatten out this curve. And now we have a situation where the curve is flattened out, but it's widened too. And now we have a much greater area under the curve here at a higher temperature of particles at any given moment which can achieve or are at or above escape velocity. So this is interesting. So we can see this difference here we get the number with escape velocity relatively lower at a lower temperature, but at a higher temperature, in yellow here, we have the greater fraction at any given time that can achieve escape velocity. So let's look at a model, a beaker full of water, for example. And a beaker full of water is nothing but a beaker full of water molecules. And here we have it just shows the water molecules within here. What I'd like to do is bring us to the air-liquid interface. The air-liquid interface. And at that air-liquid interface, we see a few molecules of water escaping from the liquid phase. Their kinetic energy is great enough so that it has exceeded that threshold, that minimum kinetic energy needed to escape, and it overcomes the intermolecular forces between those particles and then thus erupts into the into the atmosphere. We get evaporation occurring. But there are two priorities or two criteria which need to be met in order for a given particle to erupt from the liquid phase into the gas phase and thus carry out this evaporation. The first is, as we expected before, that particle must be at or above escape velocity, right there. So we saw that with our bell curve of particles, the minimum energy needed to escape. Well, that particle must be moving fast enough to have the great enough kinetic energy that it can erupt if it has the opportunity. And that's really saying something too. So let me ask you a question. What about this particle in this beaker right here? It could be moving as fast as you'd like, but it would never be able to evaporate. Why? Because it is in the middle of that column of liquid. It is only those particles that, number one, are at or above escape velocity, and number two, exist at the air-liquid interface only, that are able to evaporate. Two criteria. It's not just the fact that we have this the at or above escape velocity, but it must reside also at the air-liquid interface. So maybe we've all heard the term rate of evaporation, that some liquids will evaporate faster than other liquids or under different conditions. Well, there are three factors which affect the rate of evaporation. The first two would be comparisons of two samples of the same liquid at different conditions. And the last one is going to be two different liquids, comparing them based upon their strength of intermolecular forces. But the first criterion, which defines the evaporation rate, would be the surface area of the liquid. The surface area, that is the area of the air-liquid interface. So, and this is easily understood by thinking about if I had a liter of water in a beaker, that water, if left in the beaker, would probably take a while to evaporate, perhaps 2 weeks, maybe a month to totally evaporate out of that beaker. However, what would happen if that same liter of water, if I splashed it on the floor and it all spread out over the floor? Would that take 2 weeks to evaporate? No, it certainly would not. It would probably take about a few hours to evaporate. And the reason for that is because of that much greater surface area of the water splashed on the floor compared to the greater surface area of the air-liquid interface within the beaker holding the water. So the greater the area of the air-liquid interface, the faster the evaporation rate in that comparison. Also, and we covered this briefly on the previous slide, would be the temperature of a liquid. If I had a sample of, and I keep using the example of water, but we're very familiar with water. If I had a sample of water at room temperature and a sample of water at 10 degrees below its boiling point, at 90 degrees Celsius, well, which one would evaporate first if that 90-degree beaker were held at 90 degrees? Well, we could look at them. Out of the 90-degree beaker, we would see steam rising out. That is sort of an indicator that we have a lot of evaporation going on at 90 degrees Celsius compared to the beaker that's at room temperature. And if you came back in an hour, you would definitely see the difference in the level of the liquid within the beaker that contained the hotter sample of water, the hotter sample. So the higher the liquid temperature, the faster the evaporation rate. The lower the liquid temperature, the lower the evaporation rate by that comparison. Now, in the last two examples, we looked at two sample comparison of the same liquid. As I said before, now we're looking at two samples of different liquids with everything else, temperature, surface area, and so on, held the same. And in this case, if we had two different liquids with different particles, the stronger the intermolecular forces between the particles of one sample would mean that that sample has a lower evaporation rate, which makes sense. The particles are held together more strongly, so it takes a lot more energy to break one apart and erupt it into the atmosphere, which is actually what's going on in evaporation. This in comparison to the sample of liquid with relatively low intermolecular forces, so it doesn't take much energy to peel off one or another from that liquid sample, and thus that translates into a higher evaporation rate. So just as we had before, we had some observable features of liquids which allowed us to guess as to the strength of our intermolecular forces. Do you remember them? There was the viscosity of a liquid or the surface tension of a liquid. There are observable qualities of liquids which are used to describe the propensity of it towards evaporation. If a liquid has a higher propensity towards evaporation, it means it will have a higher evaporation rate. So these two types of qualities are known as volatility and vapor pressure. Now, the volatility of a liquid could be defined as the propensity of a liquid to evaporate. So if we had two different liquids, one would be considered more volatile if it evaporated more quickly than the other liquid. The other liquid that evaporated more slowly would be considered to be less volatile than the other liquid. The other one is known as the vapor pressure. The vapor pressure can be defined as, in a closed container, which we see here, it is the partial pressure of a liquid's vapor in dynamic equilibrium with its liquid phase. So if I take, here's a sample of water over here on the right in an Erlenmeyer flask, and if I put a cork in it, like I've done before, we're going to eventually have enough water molecules evaporate into the inside, or the trapped air in there, to have a particular vapor pressure. Do you remember when we were talking about partial pressures in any gas collected over water? That meant that there was a certain amount of dissolved water particles in that gas, evaporated particles. And this was quite well understood, and it was defined by the temperature that gas was being collected under. So at a higher temperature, there would be a higher vapor pressure of water within there. At a lower temperature, there would be a lower vapor pressure of water within that closed container. So if we want to think about this now, a liquid with stronger intermolecular forces would have a lower vapor pressure, because those particles of the liquid are not as apt to want to erupt from that liquid. They're still being held very strongly into the gas phase. So we can compare volatility and vapor pressure with our relative strengths of intermolecular forces. Remember, this is all about a comparison of intermolecular forces between two samples of a liquid, or vapor pressure, volatility, and what have you. So let's try to group these together. So these observable qualities we can group together. We have, if I have a liquid with a high vapor pressure, that means it is of a higher volatility than comparison to another liquid which of a lower volatility. Higher vapor pressure and higher volatility means the particles have lower, weaker intermolecular forces, and thus will have a lower boiling point. Those four can be grouped together. By comparison, if I had a liquid with a relatively lower vapor pressure, it would be considered to be less volatile, have a lower volatility. And this would be the result of higher intermolecular forces, stronger intermolecular forces between its particles, and thus it would have, by comparison, a higher boiling point. In the next lecture, we're going to look at some of these terms and put them together to talk about what type of physics governs these transitions, say, from solid to liquid, that of melting, and liquid to gas, that of boiling.